Okay. All right. So we're going to continue talking about sampling distributions and samples today. So if you think about what we've done in the past sections, we've talked about like the typical collection of data, the mean, stuff like that. And then we've had the proportion ones when we're looking at the percentages and those change pieces. So like we can look at like the 50-50s and those type of situations. That's what we're going to look at today. We're going to look at how we can use what we talked about on Monday's class and looking at doing a sample of information and comparing it to what we think would happen in terms of the whole population. So there's two formulas we need. The first one's pretty simple. It's just the mean. It is exactly what the proportion actually ends up being. So your mean, you do not actually have to calculate. It is just going to be whatever the proportion is. The only time you're going to have to calculate it is if they don't tell you the percentage and they give you information to find the percentage. So like if they say we're looking at getting heads on a coin, they're not necessarily telling you the percentage, but you can figure it out that heads is 50-50, so it's 50%. So that would be your probability. So your mean is just your probability. Your standard deviation is actually the exact same formula that we had before, the p times 1 minus p. The difference is we're dividing it by n like we did the one on Monday. So you're going to divide it by how the sample size that you end up having. So this is really the only formula you need. You don't need to worry about, you don't even need to worry about that one because it's the same thing. So really that is the only real formula that you need to remember and we're going to use. All right, how many people in here like Pepsi? No, Pepsi. One, that's it. How many people like Coke?
Okay, I don't like diet. I like regular.
Oh, that's fine.
Yeah.
Okay, how many of you like Pepsi products? And how we'll do the products, not necessarily just the cola. How many like the Pepsi products? Okay, how many do you like the Coke products? Sprite is Coke.
Oh, okay.
Sprite is Coke, and Starry is the Pepsi version of Sprite. So, Dr. Pepper is Dr. Pepper. Dr. Pepper is actually its own brand, and the second most popular soda now, behind Coca-Cola. Pepsi is now third behind Dr. Pepper. No.
Wait.
Yeah.
What about more Coke
All right. So, oh, nope, I don't want to change my view. I just want to break it down a little bit. All right. So, let's assume when we're looking at this Pepsi and Coke, we'll assume a 50-50 split. It's not, and we're going to find that out in a minute, but let's assume a 50-50 split. Okay, because whenever you're doing these problems with proportions, you need to know what the beginning, like what you're comparing it to, that mean of the population. So in this case, the mean of my population is going to be 50 or 0.5. So that's the first piece of information we need. Okay, which is my P. So they are taking a sample of 400 people, and they want to know what the probability that less than 0.44 of the people sampled will prefer Pepsi. Okay. So if it's really 0.5, what is the probability that less than 44% would actually prefer Pepsi? So what is going to be my N in this problem? 400. Okay, so with this information, I can now find my standard deviation. Because my standard deviation is P times 1 minus P over N. So I have 0.5 times 0.5 divided by 400. So my suggestion, so I'm thinking when I'm looking through the tests, I'm wondering how many people are getting things wrong because they were typing them in their calculator wrong. So my suggestion would be to start using Desmos, because you can type it in and have it look exactly like what the formula is. So you know you're typing it in correctly. Okay. So like you could have easily done 1 minus 0.5 and actually literally typed it exactly what the formula would have looked like. Okay. Because I think there's some situations where when you're dividing it, so if you remember, we're looking at the X or the Z score when you were doing like 45 minus 50 divided by 4, for example, things like that, you get some crazy number. And it's because of the way you were typing it into your calculator, it was doing the auto operation, so it was doing the division first. So that could have been some of the issues that I saw. Yeah.
I'm wondering, how are we still gonna have about like 14 questions on the final, or is it gonna be way more than that? The time the class runs TC for final, right? That's in that.
So the final will be a little bit longer because we have a final schedule. So your final actually will be a longer class period. You have a 3-hour window for your final, so it'll be a little longer. So I will tell you that the majority of the final will be focused on chapters 8 and beyond, because that's the more like the part of that. There will be some stuff from the beginning stuff on it, but it'll mostly be from chapter 8 and beyond. So, all right. So that is my standard deviation. One zero. So now that we've got our mean and our standard deviation, everything after this point is exactly the same as we've been doing all along. We find our z-score, we plug it in, find the percentages. So my z is x minus the mean divided by the standard deviation. So x in this case is my 0.44 minus 0.50 over 0.025. And when you type in Desmos, that's what it should look like. And we get negative 2.4. Hello. All right, so negative 2.4 is 0.0082. So if we look at our little chart, so that's negative 2.4, and we're looking for less than that. So we're looking for that piece there. And that piece there is 0.0082. And that's it. So if we change that to a percent, so we can kind of understand how it works a little bit better, we're looking at 0.8%. So is that likely to happen? No. But what if it did? What if I asked 400 people and only 44% of them like Pepsi? What does that mean? Huh? Okay, it could be. But what happens if 3 people did it and it came out to be very similar? What do you think that means? So, yeah, go ahead. Well, if we have 3 people doing, so like if it was one situation, yeah, it could have been an outlier. No. I'm talking about 3 of you did a survey. You each surveyed 400 people, and in each of you came up with a number approximately 44%. Okay, could be, depending on where you're asking the questions. However, in statistics, when we start to look at, and this is where one of the things we're going to start getting into in chapters 10 and chapters 11, is we start to make inferences. So remember, there's 2 types of statistics, right? There's descriptive, which is like your mean, modes, medians, standard deviations, stuff like that. And then there's inferential. Inferential is when you're starting to make predictions about what's going on in the population. So in this situation, if we keep getting like something around 0.44, that means my initial assumption probably wasn't correct. It's probably not a 50-50 split. It's probably less than 50% actually likes Pepsi. So when you're starting to look at certain things, like we can make a claim and we can start to use what we're doing here to test that claim. Okay, so in this case, my initial claim was that the population is 50-50 split from Pepsi and Coke. Well, based on the sample that we got here, it might not be actually true. Okay, does that make sense? So that's where we can start to go with some of this stuff. We can start to look at, is my initial assumption correct? And if not, let's go back and look at that to make some changes to that. All right. So suppose a sample of 500 is used to estimate the fraction of voters that are in favor of a particular candidate. So we've asked 500 people, and we want to know, if they're in favor of a candidate, and the population proportion that favors the candidate is really 40%. What is the probability that the error of the estimate will be less than 5%? Okay, so we're making the assumption that the actual population proportion is 0.4. We want to know what's the probability that the error of the estimate will be less than 5%. So now this is where, if you'll ever look at polling and any kind of statistics that you see, any kind of thing, survey, you'll always see them say plus or minus a certain percentage on the bottom. Okay, that plus or minus is where we get. That's where this came from. Okay, so if we look at our little bell chart, so this is 0.4 in the middle. We want the error to be less than 5% or 0.05, right? So what's the lowest number that I'm going to want here? Well, this is the actual, right? So what would be the numbers that I'm looking between? What would be the smallest I'd want my survey to come out to be? Yeah. No idea? Cool. What's 5% less than 40%? 35%. What's 5% more than 40? 45%. So if this is true, that would be plus or minus 5%. Correct? Do you understand why or no? All right. So again, we're trying to, when we're looking at all these statements, do we know if the population proportion is really 0.4? No. Because to get that exact number, I'd have to ask every single person. Okay? We'd have to ask them all. And we don't ask them all. If I was doing this lesson a week from now, I probably would have been able to use the actual numbers from the election to do this, because we have the actual proportion, just not totally finalized yet. So it's going to adjust a little bit. And we have the polling data right before the election that I could have actually used to determine if that's accurate or not. But if my population proportion is really 0.4, so that's basically going to be like kind of like my assumption. Okay. I want to know what's the probability that I'm going to get numbers between 35 and 45%, because that'd be plus or minus 5% from where I think it's going to be. Does that make sense? Okay, because my surveys are not going to come out to be exactly what the answer is. No survey is ever going to be exact. All right, you might hit it, get lucky, but the surveys typically aren't going to be exact. They're going to have some variation in them. That's where that plus or minus always comes into play. So if I got a survey that said 37%, that's within that realm of possibility. The 5%, that might be okay. So let's see what percentage of people would actually be between those two numbers. The reason we need these numbers is those are my x's to find my percentages. So we need to find two pieces of information before I can do this problem. What are the two things that I need? What are the two things I need to ever find Z? Yeah. The mean and standard deviations. I need those two pieces of information. What is my mean? 0.4. Okay, because mean is just your proportion. My standard deviation is 0.4 times 1 minus 0.4 over my sample size of 500. So 0.022. So now we can find my x. So it's 0.35 minus 0.4 divided by 0.022. So negative 2.27. And if you're going symmetrically on both sides, it should be the exact same Z. One's positive, one negative, because you're going symmetrically. All right, find me my percentages for each of those. Really? What was our percent? It's going to flash in a second. Is my computer crashed? What was the percent of the? Sure, because I'm trying to get my computer back up and. Okay, now what do we do with those two numbers? Right.
You get a 0.9768 or 97.6.
Yes. Okay, I'm just going to restart my computer. Okay. What were the two numbers so I can actually write them down now? 0.0, was it 227? 116? And the other one was, and we subtract them to get my final answer. All right. So what that means is we have a 97.68% chance that it'd be between 0.35 and 0.45. So we have a 97% chance that we're within plus or minus 5% of the actual probability in that situation, which is good. What would be the z score if it was 3%? What would change? Huh?
Less than 3%.
Yeah, between 3%. So plus or minus 3%. Just get me the z score. So what's it? Oh, hold on. You're looking at the wrong thing. So this was plus or minus 5%, right? The one we just did. So we're going to use plus or minus 3%. So it'll be 0.37 instead of 0.35. I know what you're looking up. Bless you. So it ended up being negative 1.2. So 11.507. So it'd be about a 70% chance that it'd be between, or 77% chance. Yeah.
Where did you get the negative 1.2? Because I got 1.36.
Sure. Oh,
Yeah.
there you go. That would change it. Okay, so 0.9139 on that side. So it'd be about 85% chance. So you can start to see how now that 0.022 is based on 500 people, right? Anybody remember what the number I told you how many people they normally ask in polls are?
5,000.
Huh?
5,000.
Yeah, it was like 1,000 or so. If we took the same problem, so if we made, so my mean, the mean doesn't actually matter. I mean, the proportion doesn't actually matter in this situation, but let's keep it as the 0.4. So, and my x is going to be 0.37 and 0.43. My n will be 1,000. So if we do my standard deviation, 0.4 times 1 minus 0.4 over 1,000. I probably should have shared that. There we go. My standard deviation is 0.015. So now if I find my Z, we are at -2. That means my other Z would be at +2, right? So 2 is 0.97725, and -2 is 0.02275. And if we subtract those two, we get exactly 0.95. So if I asked 1,000 people, I have a 95% chance to be within ±3% of my answer. Did anywhere in this problem ask you the number of people in the population? No. So by asking 1,000 people, I will be within 95% of my actual answer for the entire population. It doesn't matter if I'm asking 1,000 people for the entire population of the United States, 1,000 people for the entire population of Connecticut, 1,000 people for the entire population of Three Rivers College. It gives you the exact same percentage because the population doesn't matter in that respect. But what is the one most important fact about those 1,000 people? What's the key? Yes,
Have to randomly selected.
it has to be randomized. Okay, that's the key. Has to be a random sample. But as long as it's a random sample and there's no bias in it, it's not underrepresenting or overrepresenting any populations, we're good. That's why every poll you ever see says ±3% on the bottom of the screen. Okay. And if you don't see it listed there, I guarantee you it's ±3%. Because this is the numbers that they use to get them. Okay. Interesting. All right. Yeah, this one. All right, let's do one more of these, and then we'll talk about some sample methods. All right. What are the pieces of information I need to know? Okay, so and 50 would be what piece? That's my n. Okay, that's my sample size. All right, what else do we need? We need our mean or proportion. So what's the proportion? 80%. That's 0.80. They're not always going to give it to you in numbers, so just keep that in mind. Statistics seems to like English a lot. All right, and then we need our standard deviation, right? So what's going to be my standard deviation for this? Yep. Same formula. All right. So if they randomly select 50 airline flights, what's the probability that 85% of them will be on time? So that 85% is my what? That's my X. All right, so find me my percent. So find the z-score and then look at the z-score. Uh-huh. All right, so what did we get for our z-score? So if we look at 0.88, we get 0.81057, right? Oh, 6. Is that the answer? It says at least 85% of the sample flights will be on time. So is that greater than 85 or less than 85? Greater. So we have to do the 1 minus that. So the answer actually is 0.1894. The other two are done the exact same way, so we're not going to do the other two. All right, let's look at some other ways to actually get information. So far, we've really only talked about one option, right? So we've really only looked at a random sample. And that's just looking at basically all the data and just randomly picking out a group of people. And then making sure we don't have any major biases or anything else built into it. So one of the ways we can get it is known as a judgment sample. So judgment sample is somebody actually picking the information. Is this a random sample? No. Can I do any of the stuff that we've been talking about with a sample that was gotten this way? No. People do all the time. Okay. But this would be considered bad data. And that's why it's important when you look at information is to look at how they collected the data. Okay. So yes, this would not be good, and you cannot do probabilistic statistics with it. We've kind of talked about this one before. A convenience sample. Is this random? No. What is a good example of a convenience sample? Yeah.
Asking people your local convenience store.
Okay. Yeah. What's another example? Yeah. All right. Or standing at the door of the school and just asking people as they came in. That'd be a convenience sample. I like the convenience store. That was good. Yeah, it's convenient for the person who's picking up the information is why it's called a convenience sample. Again, not random. You cannot do the statistics and probability and stuff that we've been talking about with it. Okay. Again, very simple to fall into this trap and used all the time. Any kind of like online survey is a convenience sample. Okay. Because again, you're not randomizing who you're asking or anything else like that. You're just asking a bunch of people and you're going to get some answers. Okay. So not statistically viable. What about a systematic sample? So a systematic sample is if I have a list of people or a list of data and I take every 7th piece of data. Is that random?
It's more random.
Okay. What if I took the sales data from a store and it's listed in order of dates and I pick every 7th piece of information? Is that random? What would I get if I picked every 7th piece of data? So I have all the information from my store. I put it all in a sheet. It's listed by date. And I'm taking every 7th number to do my analysis on. Yeah. What's the pattern? Right. So I'm picking every 7th. Now think about dates. What happens every 7 days? It's a week, right? So if I picked every 7th piece of information, I'm picking the same day of the week. Okay. So would that give me good information? No. Okay. It could be just that day of the week is bad, like, or good. Like, we don't know. So a systematic sample can be good, can be bad. It depends on how the data is organized. Okay. So the other day I actually said we could do this. I says, but I listed all the names randomly. They weren't in alphabetical order. There was no order to my list. As long as there's no order to your list, so the list is randomized, and you do a systematic sample, you should get random data. However, if your list is organized and you do a systematic sample, you are not necessarily going to get random data. Okay? So the systematic sample can be good, can be a random sample, or cannot be based on how the data is organized originally. A cluster sample. So we're dividing the population into clusters and randomly selecting a sample of the clusters to represent the population. Typically, clusters are natural groupings of the information or the population. I think on Monday, one of the examples I gave you was a cluster sample. What would be a natural grouping of the students at Three Rivers? Huh? Well, yeah, but that's going to be, so that would be one grouping, but that'd be a very unequal grouping. Yeah. We could do majors. That'd be a natural grouping. Yeah. Credit hours. Okay. You guys are thinking way too big. Yeah. Okay.
Someone like the hallway or class.
Yeah. Classrooms. I was like, I knew I gave you an example of this. Yeah, you guys are thinking too big. When you're thinking about so the stuff that you're talking about, the vast majority of the stuff you're talking about is going to fall into the next sampling thing that we're going to talk about. A cluster is typically just a grouping. So like classrooms, those are just natural groupings. Like it's not like we have to do anything to it. In each of those groupings, there is a random selection of people. Okay. Most times in that classroom, there's going to be a mix of male and female. There's going to be a mix of different age groups. There's going to be a mix of different economic groups. There's going to be a mix in those classes. Okay. So when you're looking at clustering, you want to have those clusters be mixed in essence. Yes.
Would regions of the country be an effective like natural cluster? Because like New England has its own, our own like polity, I guess you could say. We are a distinct kind of group, but the rest of the country doesn't have that. Like Midwest is kind of nebulous, the South is kind of nebulous.
So again, going towards more of the next thing that we're going to talk about. So another great example of clustering would be blocks in a town, like just a block. All right, because again, like you can start to see how the blocks could level on not totally mixed, but it'd be a natural grouping that's there. So if I was going to go out and do canvassing, because we talk about politics and stuff like that, I might not want to sit there and go to every single house. Like I just don't have the time to ask every single house. But I can turn around and say, okay, you're going to go ask this block. So go around and hit every single house on this block. And you're going to go hit this block over here. Like, and just put 5 people on 5 different blocks. And that's going to be how I'm going to get my sample for the town. Okay, because those are just natural clusters. And I'm going to ask everybody in that cluster that same question. Okay, so that's where that clustering comes in. Now, clusters do not always have to be completely mixed, or that can happen. That's where we can get in some of that bias that might actually creep in, where people are underrepresented or overrepresented in those situations. So, but in essence, clustering sampling is a randomized sample because the cluster is now randomized, not necessarily the individual people in it. And it does make it a little bit easier to do that than looking at all individual people. It's easier to ask questions. The next one, this is the one that a lot of you guys kept dipping into. This is known as stratified sampling. So if you've ever taken a geology class or an earth science class, you think like strata, the rock strata, different layers. Same concept here. We have a lot of different layers to us. So stratas are subpopulations. They're identifying characteristics. So like major, like sex, like region of the country, like number of credit hours. Those things are all ways to identify characteristics of a person that we can then look at and break those down into population. Okay? So by definition, a stratified sampling is not a random sample that you're going to start. You're going to start with a stratified sampling, and then you're going to start with a strata, and then you're going to do sampling within those strata. So when you're looking at this, I would say, okay, this is how we can start to eliminate the bias. All right. So if we're looking at political party affiliation, okay, in different regions of the country, you're going to have different mixes. So I wouldn't necessarily say I'm going to ask all the people in the Northeast, because the Northeast tends to be a lot more liberal than the Bible Belt or the Southeast part of this country. So we can start to look at that. So we can't just pick one region to do that in, because we're not going to necessarily, we're going to have the bias still there. However, if we wanted to look at the Northeast, we can look at breaking it up by political groups, so we can then sit there and go, okay, we're going to ask a certain percentage of the left-leaning, we're going to ask a certain percentage of the right-leaning, we're going to ask a certain percentage of the people in the middle, and that's how I can then separate out and make sure I get a good mix of the population. Does that make sense? All right, so the strata is a way to organize the data, and then within each of those stratas, we do some other method to be able to pick it. Either just a pure random sample, or we could do clustering at that point. A great example of this would be, there was a problem, and honestly, I don't know which book I got it from, and I can't seem to find it now. But it was, they were looking at creating a pool in a town. So they wanted to create a new pool in the town, and they were doing a cluster sample, and they sampled a bunch of the blocks, and they got that 75% of the town wanted a pool from that information. Okay. However, when you looked at the demographics of the town, the majority of the people that they were served, there was a lot of blocks that were a lot poorer. And then there was a few areas where there was a few blocks that were quite rich. All the blocks that they chose were from the lower economic group, the poor group. Poor group didn't have pools at their houses where the rich people did. So by just the way they did the cluster sampling, they didn't actually represent the entire town. They only represented one subsection of that town. So that's where that stratified sampling would have come in. They could have broken it down by strata, by economic group, and then picked a certain percentage of the clusters in each of those areas to get a better organization or a better view of what the entire town's thought process was. Does that make sense? All right. Let's look at this one. All right, last problem. What sampling technique did he use? Or did they use? Oh, no, he said he. Okay. Why?
I don't know how to, you know what I'm trying to say.
Yeah, he just asked people who are there.
Yeah.
That would be convenient. Yes. No, you don't have to do this. The stratified is when you start to organize the people into groups first. So in this case, this is purely a convenience. He just literally decided that, oh, there's going to be a whole bunch of people at Disney World. Let me just go ask them. All right. So this was convenience. So therefore, technically, the data is bad data to begin with, but we'll keep going. What biases are presented in this data? Or possible biases in the responses? Yeah. Okay. Okay. Yeah.
A lot of people who go to Disney don't live in Florida.
Yeah. Like, unless he's asking specifically if you live in Orlando, Florida, most people he's going to get asked probably aren't from there. If I asked everybody in here, do you favor a Florida state income tax? We already pay income tax. Why don't they? Like, so, and then like, so, yeah, you have to make sure your population matches your data. Like in this situation, he's got some results, but it was a convenience sample, so it's not good, bad, or there. There's a lot of biases in situations where, like I said, that makes perfect sense. Even if people from Orlando are going there, they're probably ones that have extra money, and they may be against the taxes because they don't want to give away their extra money. But in that respect. And then we have a bunch of people going to Disney World that typically, most people in Orlando probably don't go to Disney World on a regular basis, if at all. So they probably work there. That'd be about it. So we'll go to the last part of the question. Is 50% a reasonable proportion of Orlando residents who favor a state income tax? No. Okay. For all the things we just said. All right. So you can start to see why collecting data in a proper way is needed. You can start to see why making sure that that data does not have any internal biases is needed before we can start to use that data. Okay. So if you remember back at the very beginning of the class, I told you, I says the one big thing you're going to be able to get out of this is to start looking at data with a critical eye, looking at information people are telling you with a critical eye. And that's the important pieces in this. It's like, how are they collecting their data? What did they do to make sure that data is randomized and a good data before they even did the actual study and got the information out? Because if what they did to begin with isn't good, then the data is not good at the end. Okay. All right. We are done. We are done with chapter 8 or 9, by the way.